Section 10.13, Cryptography. The study of encoding and decoding secret messages is called cryptography. In the language of cryptography, codes are called ciphers, uncoded messages are called plain text, and coded messages are called ciphertext. The process of converting from plain text to ciphertext is called enciphering, and the reverse process of converting from ciphertext to plain text is called deciphering. The simplest ciphers, called substitution ciphers, are those that replace each letter of the alphabet by a different letter. A system of cryptography in which the plain text is divided into sets of n letters, each of which is replaced by a set of n cipher letters, is called a polygraphic system. Hill ciphers are a class of polygraphic systems based on matrix transformations. As an example, how about we use the matrix 1, 2, 0, 3 to obtain the Hill cipher for the plain text message, I am hiding. So to obtain the Hill cipher, we first group the letters that we want to encipher into groups of 2. So I'll write I, A, and then I'll write M, H, I, D, I, N, and GG separately. So then I is the 9th letter of the alphabet, so I'll assign 9 to it. A is the first, so I assign 1. M is the 13th, so I assign 13. H is 8th. I is 9th again. D is 4th. I is 9th. N is 14th. G is 7. So notice I put an extra G because I want to have an even number here. So I just duplicated the last letter. Okay, so now let's encode this or encipher this using matrices. So I'm going to use the matrix 1, 2, 0, 3 and multiply it by each of these guys as matrices. So I'll take 1, 2, 0, 3 and multiply it by IA, which is 9, 1, so that I can get 11, 3. And the 11th letter of the alphabet is K. The third is C, so that gives me KC. Okay, next I will take 1, 2, 0, 3, and multiply by 13, 8 for MH, and I'll get 29, 24. 29 is too far in the alphabet, so I just basically keep going loop back around. It's 3 past the last letter. So I'll replace that with 3, 24. And I'll get C for 3 and X for 24. So then let's keep going. 1, 2, 0, 3 times 9, 4 gives me 17, 12. So that's QL. Then 1, 2, 0, 3 times 9, 14 gives me 37, 42. And again, that's past the 26th letter of the alphabet. So I see how far back, how far past 26 I am for each of them. And it's 11 for 37 and 16 for 42. So I'll take KP. And then lastly, 1, 2, 0, 3 times 7, 7 gives me 21, 21, which is UU. So altogether, I am hiding under the Hill cipher becomes K, C, C, X, Q, L, K, P, U, U. If M is a positive integer and A and B are any integers, then we say that A is equivalent to B modulo M, written A equals B mod M, if A minus B is an integer multiple of M. That's basically what we were doing over here when we were reducing these guys over here, because they were basically, the numbers we got were too big, so we essentially divided by 26 and got the remainder. So let's determine values for M that make these equivalences true. So let's see, what can we take to have 7 equal to 2 mod m? Well, if we make m equals 5, then 7 minus 2 will be a multiple of 5, because it would be exactly 5. For the second one, 19 minus 3 would be 16. 16 is a multiple of 2, so we could take m equals 2. For the next one, we could do, let's see, negative 1 minus 25 would be negative 26, which is a multiple of 26, so we could just take m equals 26. And then for the last one, 12 minus 0 is 12, which is a multiple of 4, so we could take m equals 4. Obviously, these are not the only values that would work. I could have just said take m equals 12, and that would still have worked. For any modulus m, it can be proved that every integer a is equivalent modulo m to exactly one of the integers from 0 to m minus 1. We call this integer the residue of a modulo m, and we write Zm is the set of the integers from 0 to m minus 1 to denote the set of residues modulo m. For any integer a and modulus m, let r equal the remainder of the absolute value of a divided by m. So then the residue r of a modulo m is given by capital R if a is greater than or equal to 0. So it's the remainder if a is positive. It's m minus r if a is negative and the remainder is not 0. And it's 0 if a is negative and the remainder is 0. Let's find the residue modulo 26 of 87, negative 38, and negative 26. So for a, we have that r is equal to the remainder of, let's see, 87. So what we have to do is take the absolute value of a, so that's the absolute value of 87, and then divide that by m, which is 26, because I said modulo 26. So that gives me 9, because it's the remainder of 87 divided by 26. So there'd be 9 left over if I divide 87 by 26. And that gives me, the residue is 9. Okay, so that means that I could write 87 is equal to 9 modulo 26. For b, let's do r is equal to the remainder of negative 38 over 26. Take the absolute value. So that would be, you can think of it almost like a mixed number in this case. That's 1 and 12, 26. So the remainder is 12. So we have r in this case, because our a was negative, little r, the residue, is m minus r. So it's 26 minus 12, which is 14. So we have negative 38 equals 14 modulo 26. Okay, let's do C. So we have R is the remainder of absolute value negative 26 over 26, and that remainder is 0, because 26 fits perfect. Negative 26 fits perfectly in there. So that means that R is equal to 0. And that means that we have negative 26 is equal to 0 modulo 26. If a is a number in Zm, then a number A inverse in Zm is called a reciprocal or multiplicative inverse of A modulo m if AA inverse is equal to A inverse A, which is equal to 1 modulo m. Let's find the reciprocal of the number 3 modulo 26 if it exists. So what we'll do is we'll set 3x equal to 1 modulo 26. And we'll just keep trying numbers and plugging them in until we get something that hopefully works as the inverse. So we'll try 0, 1, 2, 3, 4, 5, etc. all the way up through 26. I'm not going to write all of them, but it turns out that if you try x equals 9, then you get 3 times 9, which is 27, and 27 is actually 1 modulo 26, right? Because if you take 27 divided by 26, the remainder is 1. Beautiful. So that means that 3 inverse is equal to 9 modulo 26. So yeah, it could take a long time to find the reciprocal because you have to try a lot of numbers. So for the next one, let's find the reciprocal of the number 4 modulo 26 if it exists. So we'll set 4x equal to 1 mod 26. And we'll try 0 through 25 again because we're trying all the numbers up until 26. And it turns out that we won't get near reciprocal. But this kind of makes sense because 2 divides 4. I'll write it like this for divides. And 2 also divides 26. So 4 and 6 both share a common divisor of 2. So that should tell you that there won't be any reciprocal. Because it's divisible. Any square matrix A with entries in Zm is invertible modulo M if and only if the residue of the determinant A modulo M has a reciprocal modulo M. So that's why we care about reciprocals. A square matrix A with entries in Zm is invertible modulo M if and only if the residue of the determinant modulo M have no common prime factors. So M and the residue of determinant A have to have no common factors. A square matrix A with entries in Z26 is invertible modulo 26 if and only if the residue of determinant A modulo 26 is not divisible by 2 or 13. As we could see over here, it was divisible by 2, so we got no reciprocal. Let's find the inverse of this matrix A modulo 26. So, as we've seen previously, we can find the inverse of a 2 by 2 matrix by taking 1 over the determinant, so that would be AD minus BC inverse, or 1 over AD minus BC, times, well, we switch A and D, so we get D, A, and then we make B and C negative. In this case, we have to take everything mod 26, though. Okay, so let's get the determinant of A. So the determinant of A is AD minus BC. So that's 5 times 3 minus 6 times 2, which is 3. So that means that AD minus BC inverse, well, that'll be 3 inverse. And we calculated that earlier. We saw that that's 9 modulo 26. It's a good thing we calculated that earlier, because otherwise it would have been, we'd have to go through all those numbers from 0 to 25 in order to try to figure out what the inverse was, if it even exists. Okay, so now we have A inverse is equal to 9 times 3 minus 6 minus 2, 5, just by plugging into our formula now. And multiplying through, we get 27 minus 54 minus 18, 45. But we have to take this modulo 26. So 27 has a remainder of 1. Negative 54 has a remainder of 24 over 26. Everything's out of 26. And then negative 18 has a remainder of 8. And then 19. So all of that is mod 26. As a check, we could look at A inverse, and notice that it'll be 5, 6, 2, 3 times 1, 24, 8, 19. So we get 53, 2, 34, 26, 105. And 234 and 26 are both multiples of 26, so those are equal to 0 modulo 26. And 53 and 105 have remainders of 1. So yeah, that's the identity, mod 26. Let's decode the following Hild 2 cipher, which was enciphered by the matrix in example 6. Now that we have figured out how to take inverses of matrices with modular arithmetic, we can use those inverses to get back to the original decoded unenciphered text. So if we're using the matrix in example 6, we know that we have the inverse given by 1, 24, 8, 19. So we can take that and multiply it by each of the pairs over here in order to get the deciphered text. So for G and T, that's the 7th letter of the alphabet and the 20th. So we would multiply this by 720, and we would get 487, 436, which modulo 26 is 1920. So that gives us the letters S and T. So we keep going like this. The N and K give us 14 and 11. The G and K give us 7 and 11. Then we get 4 and 21. And last we get 19 and 11. So let's go through each of those pairs. We'll take 1, 24, 8, 19, multiply it by 14, 11. We get 2, 78, 3, 21. Modulo 26, that's 18, 9. So that gives us RI. Let's keep going. 1, 24, 8, 19 times 7, 11 gives 271, 265. So that's 11.5 mod 26, and that's KE. 124, 8, 19 times 421 gives us 508, 431. Modulo 26, that's 1415. So that gives us NO. Then 124, 819 times 1911 is 283, 361, which is 2323 mod 26. So that's WW. So we have to just kind of read through and try to put the space in ourselves, and you can kind of see that it says strike now, because we just won't use that last W it's superfluous. Added just to make it an even number of letters. In order to determine the deciphering matrix, let P1 through Pn be linearly independent plain text vectors. Let C1 through Cn be the corresponding cipher text vectors in a Hill n cipher. So not necessarily a two cipher. If P is given by P1 transpose, P2 transpose, and so on, and that's the n by n matrix with row vectors, P1 transpose, P2 transpose, etc. And if C is given by C1 transpose, C2 transpose, Cn transpose, that's the n by n matrix with row vectors C1 transpose, C2 transpose, etc., then the sequence of elementary row operations that reduces C to I transforms P to A inverse transpose. That kind of makes sense that if we're reducing to the identity, of course, we're going to get the inverse matrix. So how about we use that? The following Hill 2 cipher is intercepted. Let's decipher the message given that it starts with the word dear. Okay, so let's write out what dear is. DE is 4, 5. AR is 1, 18. So we would like to match this up somehow to IOSB. So IO is 9, 15. SB is 19, 2. So for P1, we have 4, 5. We need that to correspond to the C1 given by 9, 15. We also need P2 given by 1, 18 to correspond to C2 given by 19, 2. So how about we set C equal to C1 transpose, C2 transpose. So that'll be 9, 15, 19, 2, and P is equal to P1 transpose, P2 transpose. So that's 4, 5, 1, 18. And let's take 9, 15, 19, 2, and adjoin it with the matrix 4, 5, 1, 18, so that we can track what happens as we reduce this matrix to the identity. The matrix on the left. So let's start by multiplying in order to get the leading one in the top row. So usually we would divide by 9, but in this case we have to multiply by 9 inverse mod 26, which is 3. Multiplying by that 3 will give us that 1 that we need in order to invert the 9. So multiplying through 3 also gives us 45, and it gives us 12, and it gives us 15. So I haven't reduced those yet, but I will. And I'll just keep the second row. 19, 2, 1, 18. And just showing you the multiplication steps. So then we'll reduce 45 mod 26 and 12 and 15, etc. So really just the 45 has to be reduced. So we get 1, 19, 12, 15. So that's the result of multiplying by 9 inverse, which is 3. And then taking the result mod 26. So we got our leading 1. It's a little bit trickier because of the modular arithmetic. Let's keep going. So we'll get a 0 underneath by subtracting off 19 times that first row from the second row. So let's do that. We'll get 1, 19, 12, 15 just by copying the top row. On the bottom, we'll get 0 by subtracting 19 times the top row, but we'll also get negative 359, negative 227, and negative 267. So let's reduce those, modulo 26, and we'll keep the top row, 1, 19, 12, 15, 0, 5, 7, 19. Keep going. Now we have to get a leading one over here. Normally we divide by 5. In this case, we have to multiply by 5 inverse, mod 26, which happens to be 21. So we'll multiply through everything on the bottom by 21. So the top row stays the same. Bottom gets multiplied by 21. We get 0. I'll just take the modulus because I already know it's the inverse. It'll give me 1. And I'll reduce these in a minute because I'll get 147 and 339 after multiplying, and then I will reduce those, keeping the top the same, so that the bottom becomes 0, 1, 17, 9. Finding that inverse of 5 modulo 26 is not too much fun, by the way, but because you have to go all the way to 21, but yeah, it's part of the deal. So now on the top, I just subtract 19 times the second row from the first to get a 0, and I'll get negative 311, negative 156. On the bottom, 0, 1, 17, 9, and keep going, and reduce. We get 1, 0, 0, 1, 1, 0, 17, 9. So that gives me my inverse matrix. That means that A inverse transpose must be equal to 1, 0, 17, 9, and therefore I just have to take the transpose and I'll get A inverse. So that'll help me decipher this code. So 117, 0, 9. So how about we use that? We have IO, SB, TG, XE, SP, XH, OP, DE. So that was 9, 15, 19, 2, 27, 24, 5, 19, 16, 24, 8, 15, 16, and 4, 5. So we'll take our matrix 1, 17, 0, 9, multiply it by IO, which is 9, 15, to decipher it, and get 4, 5, which is DE, as we wanted, because the first word should be deer. So then 117, 0, 9 times SB, which is 19, 2, gives us 118, and we get that AR that we wanted. So now the interesting part is the rest of the message, because we don't know what that is yet. So 117, 0, 9 times 27 gives us 9, 11. So that's IK. Then 117, 0, 9 times 24, 5. gives 519, which is ES, 117, 09 times 1916 is 514. So that's EN, and then 117, 09 times 24, 8 is 420, which is DT, then 117, 09 times 15, 16 is 114, which is AN, and last but not least, we have 117, 09 times 4, 5, giving us 1119, and that's KS. So altogether, we have DE, AR, IK, ES, EN, DT, AN, KS, and if you read it maybe out loud, you might be able to put in the spaces and see that it says, Dear Ike, send tanks.